Neptune, the most obscure planet in our constellation that has caught the attention of most explorers and scientists for decades, was visited only once, back in 1989 by the Voyager 2 spacecraft. Then why haven't we returned since then? Neptune's thick atmosphere, consisting of helium, methane and hydrogen, along with its powerful winds reaching up to 2,000 km per hour, make landing on its surface quite challenging. Moreover, the extensive distance and limited resources available for space exploration mean that scientists and agencies like NASA must prioritize missions based on their scientific importance and feasibility. Despite these obstacles, Neptune has a unique atmosphere, with 14 intriguing moons like Triton, remarkable rings, and a magnetosphere, all of which scientists are eager to study further. Neptune has 14 known moons. Among these moons, Triton stands out as a unique celestial body, orbiting in the opposite direction to Uranus's rotation, setting it apart from other moons in the solar system. In addition to its intriguing moons, Neptune's 5 rings are faint and made up of particles of ice and dust. While not as prominent as Saturn's rings, they still contribute to the planet's beauty. Beyond its moons and rings, Uranus possesses a powerful magnetosphere dominated by its magnetic field. This interaction with the solar wind gives rise to stunning auroras that illuminate the upper atmosphere with vibrant colors, creating a mesmerizing display. Despite its remarkable features, Neptune has received less attention and exploration compared to other planets like Mars and Jupiter, which have been the focus of numerous space missions. For instance, the Cassini spacecraft spent 13 years orbiting Saturn, providing valuable knowledge about the ringed planet before concluding its mission by diving into its atmosphere. When Neptune was discovered in 1846, astronomers noticed its gravitational influence on Uranus. In 1989, the Voyager 2 spacecraft flew past Neptune, providing a direct view of its stunning blue appearance, rings and moons. During its observations, the spacecraft revealed deep blue patches in Neptune's atmosphere, uncovering powerful storms, with one being named the Great Dark Spot. The Great Dark Spot surprised scientists with its swirling winds, reaching a staggering 2,500 km per hour, making it the strongest storm ever recorded in the solar system. Interestingly, when the Hubble Space Telescope observed Neptune 5 years later, the spot disappeared, leaving researchers eager to understand this extreme wind phenomenon. Another intriguing aspect is that, despite being farther from the Sun, Voyager 2 showed Neptune to have a warmer temperature than Neptune. The reason for this additional heat remains a mystery, presenting scientists with a double puzzle they hope to solve. They wonder if solving one mystery could shed light on the other in some way. Before we go further, let's clarify what we mean by warmer concerning Neptune. As a gas giant, we cannot measure its overall average temperature on the ground, similar to how we do on Earth. Alternatively, we can only take temperature measurements at different altitudes, but these are limited to the outermost layers of Neptune. The measurements reveal that Neptune is not warmer than Uranus in reality. They have roughly the same temperature. This might be surprising, considering Neptune's greater distance from the Sun and its reception of less sunlight than Uranus. This temperature similarity suggests that Neptune emits more heat compared to the amount it receives from the Sun, unlike Uranus. Similar to Neptune, Saturn and Jupiter release 2 times the amount of heat they receive from the Sun. However, Uranus stands out as an exception. It lacks any significant internal heat source and primarily relies on solar heat. Therefore, it doesn't warm up like Neptune and the other gas giants. To sum up, Neptune manages to increase its temperature up to the level of Uranus, while Uranus doesn't have a significant internal heat source and depends mainly on solar heat. An internal heat source contracts out the primitive solar nebula. In similar terms, the heat in gas giants like Neptune, Jupiter, and Saturn refers to the heat that remained from the formation of the solar system when these planets were created. This phenomenon is known as the Kelvin-Helmholtz contraction. On planets like Saturn, Jupiter, and Neptune, all of the extra heat is gained from gravitational contraction. As the planet slowly contracts under gravity, the materials compressing inwardly convert its energy from potential to thermal energy, which is then released into the planet. However, the reason why Uranus lacks much of the internal heat source is not entirely clear. There might have been a factor that hindered this process on Uranus, possibly a collision early in the development of the planet that knocked it on its side. One possibility is that heat may be trapped in Uranus's interior at a constant rate and is not getting released as rapidly as it should. These ripples could be convection, happening in rare and silent episodes. To better understand this process, scientists would need to observe one of these convective sections taking place. The age of the planet and the rate at which it releases heat plays a significant role in determining the amount of heat it radiates, as older planets tend to be colder. The rate of heat release depends on various factors, including the planet's interior structure, cloud layers, composition, and convection, which can be quite complex. Gas giants like Uranus and Neptune might have more helium rain in abundance, which can affect the heat being emitted. It's possible that Uranus and Neptune have different ages, or the event that made Uranus tilt on its side may have disrupted its interior structure and made it emit more heat than it should have. Regarding the fierce winds on Neptune and Uranus, their temperatures might play a role. Heidi Hammel, a planetary astronomer who has extensively observed and studied Neptune and Uranus, speculates that the extreme coldness might create an almost frictionless atmosphere and cause faster winds. As Heidi Hammel explains, the fierce winds on Neptune might result from its landscape lacking obstacles like mountains or hills, allowing the winds to flow freely. However, the storms on Neptune could also be related to its internal heat source and the delicate balance between heat and the sunlight it is receiving from the sun. Studying the effects of these factors is challenging due to the long timescales involved. A year on Neptune is equivalent to 165 Earth years, making it difficult to observe its seasonal cycles with modern tools. While there might be a theory that suggests more solar energy leads to more wind energy, Earth has shown that only a tiny fraction of solar energy is converted into kinetic energy, or wind, in the atmosphere. Earth's solid surface dissipates wind energy through friction, leading to weaker winds compared to gas giants, which lack a solid surface and thus have much stronger winds. Neptune's extreme conditions make it inhospitable for life on its surface or in its atmosphere. With a minimum temperature of about minus 330 degrees Fahrenheit, no essential gases like oxygen, powerful winds reaching up to 2,000 kilometers per hour, and intense radiation belts from its magnetosphere, Neptune presents a harsh and challenging environment. Its lack of a solid surface covered by dense clouds further adds to the enigmatic nature of this distant ice giant. There is a slim possibility that life might exist inside Neptune. Scientists speculate that a layer of liquid water could be sandwiched between the icy upper mantle and the rocky lower core under high pressure and temperature. This liquid water layer could potentially provide a medium for chemical reactions and act as a solvent for organic molecules. The heat from the core could also serve as an energy source for any potential life forms, and the planet's magnetic field might offer protection from cosmic rays. However, it's essential to remember that this idea is highly speculative and uncertain. Moreover, many challenges and unanswered questions remain regarding this hypothesis. How would life emerge and survive in such a hostile environment? How would it get nutrients and dispose of waste? How would it communicate and evolve? Detecting and studying potential life in such a distant and harsh environment would be incredibly difficult. Another approach to exploring the possibility of life on Neptune is by studying its moons, particularly Triton, the largest and most intriguing one. Triton stands out in our solar system as one of the few places that possesses both an atmosphere and an ocean, which are important for life. Triton's thin atmosphere contains various gases like methane, nitrogen and traces of carbon dioxide and carbon monoxide, and its geologically active surface displays fascinating features like volcanoes, geysers, craters, plains, ridges, and valleys. Additionally, scientists believe that Triton might have a subsurface ocean of liquid water, possibly heated by tidal forces. It also has a temperature of about 390 degrees Fahrenheit. These features could offer benefits to potential life forms, with the atmosphere potentially protecting from radiation and meteorites, while the ocean could have hydrothermal vents serving as an energy and nutrient source. Triton's geysers also play a significant role in the search for life. They eject water vapor and organic molecules into space, potentially detectable by spacecraft or telescopes, providing clues about this distant moon. However, until further exploration and observations are conducted, the presence of life on Neptune or its moons remains a captivating but unproven possibility. However, it's crucial to recognize that finding life on Triton presents many challenges and uncertainties. Its thin and cold atmosphere with low pressure makes exploration difficult. Triton's atmosphere is very dark and deep, and the presence of frozen nitrogen and methane on its surface might limit material exchange between the ocean and the atmosphere. Additionally, Triton's retrograde and eccentric orbits could lead to instability and potential collisions with other moons. A mission to Neptune and Triton is no simple task. The long travel time of around 12 years from Earth to Neptune, using gravity assistance from other planets, poses a significant obstacle. Moreover, the harsh environment around Neptune, with extreme cold, pressure, and radiation, adds complexity. The communication delay of about 4 hours between Earth and Neptune makes controlling and monitoring the spacecraft during the mission challenging. And such a mission is very cost-intensive and requires proper planning and lots of resources. And that brings us to the end of this video. If you like this video, click on the screen to watch other videos like this one. Don't forget to like, subscribe, and click on the notification bell to get notified when we post a new video.